Go ahead.
Well, welcome to our latest episode of nanoCHAT PuBCLuB, an Ionic Viper video series in which members of the community share about their recent publications. I'm Joanne Stewart from Hope College in Holland, Michigan, and I'm your host. Today, I am joined by my good friend Ann Bentley from Lewis and Clark College to discuss her recent publication written with Sarah Scrabelak from Indiana University and published in the Journal of Chemical Education. The title is A Primer on Lattice Planes, Crystal Facets, and Nanoparticle Shape Control. A link to the publication can be found in the description that accompanies this video. So welcome, Ann. And I'd like to start with just if you could explain to us the context from which this paper emerged and a little bit about your motivation for writing it.
Sure. I have taught a nanomaterials kind of chemistry course for a number of years and found that the topic of lattice planes comes up in that course, but also in teaching X-ray diffraction in inorganic chemistry. And I never really found a good resource for explaining lattice planes and Miller indices to students. And at the same time, I've always been interested in nanoparticles and the control of their shape. So last academic year, I was on sabbatical in Sarah Scrabelak's group at Indiana University.
Yay, sabbatical.
Yay, sabbatical. And that gave me the mental space to kind of bring all that together and realize that the world, I felt, needed this kind of article that pulls all of these topics together into one article. So the article has content aimed at, and I'll describe this, but Miller indices and lattice planes, but then the broader application is in how to control the shape of nanoparticles.
So I first learned about Miller indices in physical chemistry as an undergrad, and from talking with other folks, that might have been a little bit unusual. When did you first learn them?
I don't remember, but if you look at the ACS guidelines and the concept maps of content, the Miller indices do lie in the PChem realm, especially with X-ray diffraction, and you can find it a little bit in some PChem textbooks, but inorganic solid state materials folks, you need it just as well. So.
Yeah, absolutely. So could you then summarize the major parts of the paper for us?
Sure, and I am going to share screen.
Okay.
Ooh. The paper has gone on. There it is. Okay, I was going to say gone on hiatus. All right, so you can see this okay?
Yep.
Right, so the table of contents image here talks about some models that I can show later that we developed that help show the nanoparticle shapes. But one of the first ways to start thinking about lattice planes to me comes from being a tourist, and these pictures here I took while on a bike ride, like more than 10 years ago. But these are tree seedlings. People seem to think they might be hazelnuts or filberts. This was in Western Oregon. And if you look at this field from one angle, you can see one set of lattice planes. But if you shift your perspective just a little bit, you can see another set of lattice planes. And I'm always taking pictures like that to try to explain to students what we mean by the concept of lattice planes. So the C part of this image here shows how this would be applied to a crystal lattice, which is a repeat unit of atoms. And then in the article, I did want to get into the nuts and bolts of how are these numbered with Miller indices, which is this set of 3 numbers that describes how the slices are divided throughout the crystal. So there is some content defining and indexing lattice planes and crystal facets. Basically, you're looking at where a representative plane intersects the unit cell along the unit cell lattice parameters A, B, and C. Little small example here that's hard to read in figure 2C shows intersections at A over 1, B over 2, and C over 3, which leads to a 1, 2, 3 naming system. So if people have always seen these little addresses and not been understanding what they mean, the article gets into a lot of detail about that. It also talks about one of my favorite things is table 1. you can have parentheses, you can have squiggly brackets, you can have square brackets, and you can have these caret kind of brackets. And all of those brackets mean different things in terms of what they're referring to. So I just wanted everybody to know how this works.
Yeah, and that part was mostly new to me, and I thought the picture did a really good job of capturing what each of those meant. So that was great.
Yeah, and I feel like I've seen, and people may be getting better at this over time, but early, and maybe it was just early on in nanomaterials publications, it felt like people just kind of chose randomly almost to me, like what they were using. So, and it can be a little confusing whether you're talking about a single set of parallel planes or a family of equivalent sets. That's a fine distinction. But so then once you understand these fundamentals, the next part of the paper, the rest of the paper is focused on also giving kind of almost a review. I would say the first half is like a tutorial, and the second half is a bit of a review article written for a very general audience about how differences in surface energies between these planes can be used to control the growth of particles. Briefly, there are some calculations included in the supporting info, which I've always had my students do in class, that shows different densities of atoms on different planes. And that leads to differences in surface energy in terms of how many bonds need to be broken to form a surface. And what that means is that nanoparticles, as you see here in the third line, of different shapes are exposing different planes to the surrounding world, and that can really affect their chemistry. And finally, this image here, scheme 1, shows how additives can be used to alter the relative order of energies of the different facets. So in any case, the lowest energy facet is the slowest growing of all the facets, but if you can alter and adjust the relative energies, you can control what the shape of the particle is. And that's just one way that shape can be controlled in nanoparticles, but it's classic, like very classic, and a nice way to bring in some of these topics.
And the thing that I found counterintuitive, and don't laugh at me, was, and I had to read it 3 times, was the fact that the higher energy faces grow faster at facets, and that made sense to me. And so I thought, well, then those are the facets you're going to get. And it's the opposite of that. So basically, as they grow, they sort of like fill in, and they almost leave. Maybe you have a better way to explain it. They kind of leave behind the lower energy face as the face that actually ends up on the nanoparticle.
Right.
Yeah.
It's like they grow themselves out of existence.
Yeah.
I agree that that's counterintuitive. I always thought that was confusing too. Yeah.
So I thought that was something that I really learned from this paper that was really interesting.
Yeah. Let me show you my models since I can here.
Okay.
So I actually started making the models when I was doing research in Sarah's group, because I was looking at transmission electron microscope images of shapes, and those are like shadows of the actual shape. So I wanted some 3-dimensional models to help me understand how can an octahedron look like a hexagon, which is a whole different story. But I ended up making, out of paper, and this was modeled after another JChemEd article that I had loved from 20 years ago, where they made unit cell models. But anyway, we have an octahedron, we have what do we have? A cube, and everybody's favorite, most complex, is the rhombic dodecahedron. So these are the 3 shapes that were highlighted in the article.
Oh, I didn't know they show the 2-dimensional packing on them.
Yeah, I made it so that one face, if you print double-sided, one face as an example shows the 2-dimensional. Yeah, it's very distinctly, it's noticeable, the differences in densities, the 2-dimensional densities. And then I really, with a lot of help from folks in 2 different IT departments, worked on 3D printing models. So these are actually, I should show you first that when you do a 3D print model, this one has not yet obtained any color. This is a rhombic dodecahedron, but then for the purposes of the article, I painted these 3 into different colors just to be consistent with the colors.
Oh, and they match the colors in the article. That's very good. And I'm assuming, again, the 2-dimensional, the faces actually show the packing of the faces.
They do. Yeah,
that's amazing.
It's really fun. Yeah. Students love these. They're the new fidget spinner. So if you have someone in your office hours, they can just play with the models and they really like it.
So tell me a little bit then about sort of the implications for teaching. So where might this be used? How could I incorporate it in my class?
Right. Yeah. Well, I think the fundamental knowledge in the tutorial part is great for any X-ray diffraction applications when you're talking about that as a technique. The nanoparticle and shape control in chemistry curricula can fall through the cracks a little bit. I'm lucky to have an advanced class in nanomaterials chemistry, but a lot of people have taught it at an earlier level too. And I find the geometry of this is very appealing and it can be simplified quite a bit. So I think I use it as the first module in my nanomaterials class, which I am about to go teach today with the models.
Oh, that's great. Yeah, so I teach sort of, close packing and stuff. And I do like the fact that, um, I like the way of thinking about the faces let you look at whether it's a cube or an octahedron, depending on which way, and so the octahedron kind of shows the close packing and the cube does not, so that's really cool.
Mhm. And I should say they're all face-centered cubic gold and other noble metals. That's the packing structure, but it's these different ways it could be sliced. Yeah.
Different facets, yeah. So is there, before we, I just think that's a really helpful, really interesting article. I am going to use parts of it in the spring when I get back to teaching inorganic again. I'm looking forward to that. Is there anything else that you'd like to say about the paper before we finish up here?
No, I would just say ask anyone to reach out if they have questions, and I hope it's useful for people for sure.
All right. Well, thank you, Anne, and thanks to everybody who's watched this video on our YouTube channel. If you have any questions or comments about the publication for our guest here, please feel free to start a discussion on Ionic's Discord server, which is called the Viper Pit. You can also contact Ionic if you'd like to be a guest on a future installment of nanoCHAT Pub Club. So we welcome the opportunity to learn about papers that you have published. And be sure to join us for our next episode. Thank you.
Thanks, Joanne.